In this video, we'll review some of the right angle trigonometry that you've seen before. So we'll start with a right angle triangle, a right triangle, meaning it has a 90-degree corner, or one of the angles is 90 degrees. When we label a right angle triangle, we're always looking for the hypotenuse. So the hypotenuse is always at the opposite end of the triangle from the right angle. So here's the right angle, we go across to the opposite side, and that gives us the hypotenuse. The other two sides are often called legs. Let's try that again. Legs. There we go, legs. So there would be a leg, and here's a leg. Might call one the longer leg and the other one the shorter leg. Generally speaking, it doesn't really matter, but the important part here is the hypotenuse. Before we get into the trigonometry portion, I think it's useful to talk about similar triangles. So similar triangles would be something that you've looked at before. Basically, similar triangles are triangles that have the same shape but different sizes. So they're basically a scale version of the other. So on the left here is a small triangle, on the right is a large triangle. It's kind of like we've taken a picture on a photocopier and we've just kind of enlarged it or shrunk it down. The shape doesn't change, but the size does. One of the things that you'll notice in these two triangles is that the corresponding angles are equal. So for example, we have the 90-degree corner here in the bottom left, same on this triangle here, and that means that the angle here is 60, the corresponding angle is the same, and the angle in the top portion is 30, as is the corresponding angle on the other side. Now the really useful piece of information here is that the ratio of corresponding sides are equal for similar triangles. And what I mean by that is that if we take this side length AC, this side length here, and divide it by AB, which is over here, we'll get 1.74. If we do that same thing on the larger triangle, 7.8 divided by 4.5, we will also get 1.74. So it doesn't matter what size the triangle is, as long as the angles are the same, the ratios of the side lengths will be the same. And that's kind of the basis for all of the trigonometry work that we're going to do shortly. So we'll use our calculators to help us, but the calculator uses this idea that similar triangles have corresponding side lengths or ratios of corresponding side lengths that are the same. All right, let's get into some of the details here. So we're going to talk about the primary trigonometric ratios, primary trig ratios for short. The three primary trig ratios are sine, often abbreviated just SIN. We still pronounce it sine, but we just write it SIN for short. Cosine, which again we would write as COS for short, and tangent, which we write as DAN for short. And these three trig ratios are used to find missing side lengths or missing angles in right angled triangles. Now probably you've seen these ratios before. Before I get to those, we're going to start with this triangle here, triangle ABC. We have an angle indicated in the bottom right. This angle here is called theta. You can see that by the little Greek symbol theta there. We could use any variable or letter that we choose, but in this case it's showing as theta. When we do this right angle trigonometry, the first thing we want to do is label the triangle with respect to the angle that either we're given or that we're trying to find. I always start with the hypotenuse. We talked earlier about how the hypotenuse is opposite the 90-degree angle. So here's our hypotenuse, and I'll just use the three-letter abbreviation for the hypotenuse just to keep things nice and simple. Here's the angle that we're interested in, and so from the angle that we're interested in, the side length at the opposite end of the triangle is called the opposite side. Again, I'll just use OPP for short. That is a very bad looking P. Let me fix that up for you. So OPP for opposite, and this side that makes up the angle that isn't the hypotenuse is called the adjacent side. So we're going to use this information and we will find the missing length in a triangle. So here we have a triangle in example 1. We are given an angle here of 35 degrees. We know the side length is 20 and we're trying to find the other side length. So the first thing we want to do here is to label this triangle. So here's the 90-degree angle. I'm going to go across to the opposite side. That is the hypotenuse. Here's the angle that we're given. Across to the opposite side, that is the opposite side. and the other side is the adjacent side. So now that we have the triangle labeled, we want to determine which of the three ratios, sine, cosine, or tangent, we can use. Well, in this triangle, we are given the hypotenuse and we are asked to find the adjacent. So we look at the ratio that has the adjacent and the hypotenuse, and you can see here that's this one right here, which is the cosine. So that's a key step there, is to look at the information that you're given and use that information to find some values here. So we know that the cos of theta, I'll just rewrite that, cos of theta, and again I tend to write it in short form just to save a little bit of time, is the adjacent divided by the hypotenuse. Oh, sorry about that. Having trouble with my penmanship today. And then we just fill in the values that we know. We know the angle theta, here's our angle theta, is 35 degrees. So the cos of 35 is equal to the adjacent side, which we don't know. It's already labeled as a variable a, lowercase a for side lengths, uppercase for angles, divided by the hypotenuse, and we know that the hypotenuse is 20. So at this point we have an equation that we can solve, and the way that we are going to solve that equation is isolate the variable a. A is being divided by 20. To undo that division by 20, we do the inverse operation, which is multiplying by 20. I don't know if this is going to fit in here. I multiplied the right side, so I also want to multiply the left side, and I'll just try to squeeze a 20 in there. There we go. So 20 times that. So now we can go to our calculator. I'm just going to rewrite that so that you can see it a little bit better. So we have 20 cos 35 is equal to a. And then we can plug that into our calculators, and we should get an answer that is something like 16.4 or thereabouts. Now you should make sure that your calculator is in degrees and not in radians. That's usually indicated by a D or a DEG for short. If it says R or rad or G or grad, you'll need to find a way to change that into degrees, because if it's not in degrees, you'll get the wrong answer. So there's our first example. We found the missing side length. A is equal to 16.4. So this side length here would be 16.4. The units would be feet, since the other side length was also measured in feet. All right, we'll do two more examples. This one's a little bit different. So the indicated side length here is x that we're going to try to find. It might, on the surface, look the same, but as we get into it, you'll see it's a little bit different. So again, I'm going to start the same way. I'm going to label my triangle. Here's my 90-degree angle. The opposite side from that is called the hypotenuse. Here's the angle that I'm using. The opposite side is over here. And the last side is the adjacent side. And you'll see here that we have the opposite side, and we are trying to find the adjacent side. I'm just going to go back one slide. Opposite and adjacent, you can see here is tan, so that's the ratio that we want. So tan theta is going to equal the opposite side divided by the adjacent side. Whoops, I lost my theta here. There we go, tan theta. Now we can just plug in the values that we have. So tan 60 is equal to the opposite side, which is 4 over x. Now you'll notice in this case the variable that we're trying to solve for is in the denominator. That makes things a little more challenging. It's not impossible, but that's why I wanted to show you this one. So our first step here is to get rid of the x in the denominator. We can do that by multiplying both sides by x. Multiply that side by x. Multiply the left side by x, and then we're left with x tan 60 is equal to 4. And again, remember, our goal is to solve for x. We want to get x on one side all by itself, in the numerator ideally. And then from here we can just divide both sides by tan 60. Again, I could have gone to my calculator and plugged that in right away. I didn't want to carry a bunch of decimals or anything, so I just did the algebra here. But if you're more comfortable doing that, by all means, go ahead. So now we get x is equal to 4 divided by tan 60. And again, maybe I'll just rewrite that so you can see our simplified version. 4 over tan 60. And then again, making sure your calculator is in degrees. You should only have to change it once, but when we do that, we should get that x is equal to 2.3. There weren't any units here. This side length here is 2.3 units. All right, and the last thing we want to do is to find a missing angle. So here's a triangle. It has two sides labeled, and we're trying to find this angle A down in here. So again, we'll start the same way. We'll label the triangle. Here's the hypotenuse. Here's the opposite side. It's opposite the angle that we're given, we're trying to find. And then finally, we have the adjacent side down here. So in this case, we have the opposite and the hypotenuse. The trig ratio that uses opposite and hypotenuse is sine. So opposite divided by the hypotenuse. And we'll just plug in some values. We don't know what the angle is. I guess it's labeled A, so we may as well label it sine A is equal to the opposite, which is 12 feet, divided by the adjacent, which is 25 feet. Now, in order to solve for A in this case, what we want to do is we want to undo this sign here. And the way that we undo a sign is with the inverse sign. So we take the inverse sign of both sides. I'm going to write this out the long way just once so you can see it. So we're taking the inverse sign of that angle that we had, or of that left side of the equation, which was sine A. And the inverse and the function sine undo each other. So when we do this, we're just going to be left with A. I don't expect you to write this out. I just want you to see the connection so you see what we're doing here. So if I take the inverse sine on the left, we better do the same thing on the right. And on the right side, we had 12 over 25. Oh, that's a big bracket. Let's try that again. There we are. So the inverse sine and the sine will undo each other. That'll leave us with A on the left side, and on the right side, we'll do the inverse sine of 12 over 25. Type that into your calculator. For some of you, that will be exactly as it appears. So shift sine, shift or second function sine, bracket 12 divided by 25, and close the bracket. For some of you, you have to kind of type it in the opposite order. So it'll be 12 divided by 25, press the equals button, and then press the shift or second sine button. And you should get an answer of approximately 28.7 degrees. I did round that to the nearest tenth there, but you should get something like that. If you're having a hard time, let me know, and we can kind of figure out what's going on. All right, so in a nutshell, there's 3 examples that show you how to find missing side lengths and angles in right-angled triangles. I do want to mention a couple of other things, actually just one more, I guess. There are some angles that we use so commonly that we call them special angles. And those angles are the 30-degree angle, the 45-degree angle, and the 60-degree angle. And so we have these 2 triangles that allow us to kind of work with this. If we wanted to, we could construct these 2 triangles. I think we'll save that for later if we get there. This triangle, I'll start with the second one, is an isosceles triangle, which means it has 2 side lengths that are the same. It is a right triangle, so the angle in here is a 90-degree angle. So if these 2 side lengths are the same and this angle is 90, that means that each of the angles here must be 45 degrees. We could go ahead and use the Pythagorean theorem to figure out what this side length would be if these side lengths were 1. I think, again, we'll just save that for later, but just know that these 2 special triangles help us determine the ratios for these angles that are so common, the 30, 45, and 60-degree angles. So we can use this triangle. So if I wanted to find the sine of 45, the sine of 45 is always the opposite side divided by the hypotenuse. So we would get 1 over root 2. If you look here, you can see that that is in fact the sine of 45 degrees. And we can do the cosine, which would be the adjacent over the hypotenuse. Notice we get the same thing. And the tan would be the opposite over the adjacent, which would just equal to 1. And we can do that for all three of these angles and all three of the ratios. So typically in a class, familiarizing yourself and getting comfortable with these values is going to be kind of important. So there it is as an introduction. We'll see them again at some other point. So there's your introduction, review of introductory right-angled trigonometry. Some of you may have used an acronym, the Sohcahtoa, very common to use, just to help you remember which ratio to use. I tend to write it like this. So the sine is the opposite divided by the hypotenuse, cos is the adjacent divided by the hypotenuse, and tan is the opposite over adjacent. So certainly if that's something that that little mnemonic can help you, then by all means go ahead and use it. And that's it for introductory trig.